proofs given in previous examples are typically called combinatorial proofs. In general, to give a combinatorial proof for a binomial identity, say A equals B, you do the following. First, you find a counting problem you will be able to answer in two ways. And then second, explain why one answer to the counting problem is A. Third, you explain why the other answer to the counting problem is B. Since both A and B are the answer to the same question, we must have that A and B are the same. The tricky thing is coming up with the question. This is not always obvious, but it gets easier the more counting problems you solve. You will start to recognize types of answers as the answers to types of questions. More often, what will happen is you will be solving a counting problem and happen to think up two different ways of finding the answer, and boom, you have a binomial identity, and the proof is right there. The proof is the problem you just solved together with your two solutions. For example, consider this counting question. How many 10-letter words use exactly 4 A's, 3 B's, 2 C's, and 1 D? Now let me write this on my whiteboard here so you can keep track of that. Okay, so we have 10 letters. So how many 10-letter words where we use exactly 4 A's, 3 B's, 2 C's, and 1 D? Let's try to solve this problem. We have 10 spots for letters to go. 4 of those need to be A's. We can pick the 4 A spots in 10 choose 4 ways. So again, there are 10 total locations here. And we can pick the 4 spots to put our A's. There are 10 choose A ways of doing that. So let's say we put the A's here. There are 10 choose 4 ways of picking where the A's go. Now, where can we put the B's? Well, there are only 6 spots left. We need to pick 3 of them. This can be done in 6 choose 3 ways. So maybe we put the B there, there, and there. So there are 6 choose 3 ways here. I'll put this over here. The 2 C's need to go in 2 of the 3 remaining spots. So we have 3 choose 2 ways. I'm going to move this real quick so that you have more room to see here. There we go. So for the C's, we had 3 spots and we picked 2 of them. And then, so there are 3 choose 2 ways of doing that. That leaves just 1 spot for D, but we can say that we have 1 spot to place to choose 1 location for that spot. Thus, the answer is 10 choose 4 times 6 choose 3 times 3 choose 2 times 1 choose 1 by the multiplicative principle. But why stop there? We can find the answer another way too. First, let's decide where to put the 1D here. So we have 1D, and we're going to try to figure out where to put that D. Well, there are 10 spots. We need to choose 1 of them. So this can be done in 10 choose 1 ways. So let's say we put the D like maybe there. Next, we're going to pick the C's. There are 9 spots, and we need to choose 2 of them to be C's. This can be done in 9 choose 2 ways. And similarly, we now have 7 spots, and 3 of them need to be filled with B's. So maybe we put our C's here, And now we need to fill 3 of these remaining 7 spots with B's. Maybe there, there, and there. There are 10. Now there were only 7 spots remaining, and we wanted to position 3 of them. We wanted to choose 3. So there are 7 choose 3 ways of doing that for our B. Finally, the A's can be placed in 4 choose 4 ways. We have 4 spots remaining and 4 A's. And so we are taking 4 positions and we're choosing 4 of them to be A's. Okay. This gives us the binomial identity that these two things, these two numbers must be the same numbers because they're the answer to the same question. And I don't know if you can tell, but there's a relationship between these binomials and how they're ordered. And you can probably generalize how these two binomials are equal to each other. Maybe instead of using specific numbers, you use variables like n, or I guess just indeterminates like n. Now, here is another example with more binomial identities and combinatorial proofs. First, I'm going to erase everything here. There we go. I actually have my question up here. We're going to prove this identity, which says 1n plus 2 times n minus 1 plus 3 times n minus 2 plus all the way up to n minus 1 times 2 plus n times 1 equals n plus 2 choose 3. All right, so we're actually going to answer this question or prove this identity by answering a different question twice. And we're going to show that those two answers therefore are the same. So in this case, we're proving that two things are equal to each other. And so we need to answer this question, not this question, but a totally different question. And we have to answer them in these two ways. So this is sort of strange, but instead of addressing this question and proving this, we're going to now completely come up with a new question where these two sides are the answers to that question. Okay, well, how do we know which question to ask? And how do we know that these two are going to be the answers to that question? Again, that's a tough thing. You learn that over time. And so practice makes perfect. That's why we're here. All right, so first off, I'll give you my approach to this. Well, I notice that this left side here is kind of crazy, and I don't really know problems that involve all that fancy stuff, right? However, on the right side, it's a little simple. It's just n plus 1 choose 3. Well, I can come up with a question that has that as my answer, n plus 2 choose 3. Let's say we have, we're trying to find the number of 3-element subsets to the set containing n plus 2 objects. Okay, so let's write that down real quick. So let's look at the set 1, 2, 3, all the way up to n minus 1, n plus 1, n plus 2. Okay, so this is our set, and we want to find all the subsets of size 3, of cardinality 3. Well, how many ways can we do that? Well, to find a 3-element subset, maybe it would be like 1, 4, and n or something like that. That's one 3-element subset. How many 3-element subsets are there of this set? Well, that's the question that I'm framing here, and I'm actually going to answer this question twice in 2 different ways. The first way is that way. We know that the answer to this question is n plus 2 choose 3. We just have all of these n plus 2 elements and we choose 3 of them for our subset, our 3-element subset. So that's one answer. Now let's answer this question in a different way, and somehow we need to construct that solution. Well, it's not super obvious on how to do that. That one takes a lot of time and skill to develop an understanding of where you come up with this solution. So I'm going to work this one with you because I don't expect anyone to just jump into, oh, I know how we get that. We just have to answer this question in this way. No, I don't expect you to do that yet. That'll come over time as you get better at these questions and do more practice. So how do we do this? Well, here's what we're going to do. We're going to look at our 3-element subsets. So we have A, well, that's a really bad subset symbol. A, B, C. These are our 3-element subsets where we can pick a number for A, a number for B, a number for C. Now, to avoid counting multiple subsets the same over and over again, we don't want to double count anything. Let's just make sure that A is less than B, which is less than C, so that they're in order. So here's what we're going to do. We're going to count the number of 3-element subsets in a very long fashion. This is going to be a little strange on how you would approach this. What we're going to do is we're going to first pick B, and then we're going to find how many different ways we can pick A and how many different ways we can pick C. So first, let's pick B. Okay, so what does that look like? Well, let's start with B equals, well, 1. Can B equal 1? No, that's not possible because then what would A be? So B can't be 1. That's not possible because A has to be less than B. So that is not, we can't have the scenario where B equals 1. So let's ignore B equals 1 because that's not possible. What about B equals, and I know this might seem oddly specific, but let's say B equals n plus 2. Can that happen? Well, no, because then what are you going to pick for C? Because it's got to be a 3-element subset, and n plus 2 is the last number in that set, and C has to be greater than B. Can't do that. So B cannot be 1, and it cannot be n plus 2. But it could be any number in between. It could be 2, it could be 3, it could be 4, it could be 5, it could be n minus 1, n, it could be n plus 1, but it can't be n plus 2 because then we're going to mess up C, and it can't be 1 because that's going to, B equals 1 is going to mess up A. All right, so B can be anywhere between 1 and n plus 2. What we're going to do is we're going to go through each scenario. Let's start with B equals 2. So if B equals 2, what does that mean? What do we know about this specific subset? Well, we have some information about it. Number 1, we know information about what A has to be. A has to be 1 because that's the only option. If B is 2, that means A has to be 1. A cannot be any number other than that because A is less than B. Okay, so A equals 1. What about C? What else do we know about C? Well, for C, C could be any number between 3 and n plus 2. It could be any number there. How many different numbers can C be there? Well, in that scenario, it is n minus 1. There are n minus 1 numbers between 3 and n plus 2 inclusively. So in that scenario, we have a total of, what is that? Sorry, there are n choices. I got that wrong. It's not n minus 1 choices for C, it's n choices. So there is 1 choice for A and n choices for C. All right, let's go to the next scenario. So we looked at all the cases where B equals 2. What about if b equals 3? Well, let's start with a. Starting with a is a little bit easier in this scenario. What can a be? Well, a can be 1, but it could also be 2. So there are 2 choices for a. And then for c, there are n-1 choices. In this case, because b is 3, that means c has to be between 4 and n plus 2, which there are n-1 ways of doing that. So that means that in this scenario, there are 2 times 2 choices for a and n-1 choices for c. Okay, so we've counted all the 3 element subsets where b equals 2, or b equals 3. We could do it for b equals 4, and so on. We can do it, in fact, all the way up to b equals n plus 1. What would that look like? That means the total number of ways here. So in the first scenario, if b equals 2, there are 1 times n ways. When b equals 3, there are 2 times n-1 ways. When b equals 4, you're going to guess that there are, that should be an addition, 3 ways of choosing a and n-2 ways of choosing c. When b equals 5, there are 4 ways of choosing a and n-3 ways of choosing c, and so on. And eventually we're going to get up to, I think it's, n-1 choices for a and 2 choices for c, which is just the reflection of that one right there, that term. And then finally, last but not least, oops. Sometimes that happens, sorry. The last option here we have is where I think we have n ways of choosing a, and c has to be the last position there, or the last number, n plus 1. So there's only 1 way of choosing c. Now, if you notice, this right here is our answer to how many 3 element subsets there are for the set 1 through n plus 2. Okay. Wow, okay, so what does that mean? We have, this is the answer to our question that we came up with, but also that right there is the answer to our question that we came up with. N plus 2, choose 3. That way is a little bit easier to address this problem. But here is the point of this question. We answered this question in 2 different ways, but it's the same question in 2 different answers, which means that these 2 answers have to be the same. And so because of that, that means that 1n plus 2 times n-1 plus 3 times n-2, this left-hand side must equal the right-hand side. And so we answered this weird question, but the purpose of what we're doing here is not to answer the question that we come up with. How many ways can we make 3 element subsets for 1 through n plus 2? We're not trying to do that. That's not the goal. The goal is to answer that question in 2 different ways, thereby showing that those 2 answers are the same, and thus proving an identity about those 2 specific things. So again, combinatorial proofs are kind of weird. We're proving an identity by coming up with a random question and answering that question in 2 different ways, thereby showing those 2 answers are the same. So again, the point is not to answer the question. The point is actually to create the question and then answer it in 2 different ways to prove an identity about binomials. And in fact, in combinatorics, you might want to prove a lot of things other than binomials. You might want to come up with some crazy identities about factorials or so forth, which we'll get into later on in this course. Anyways, thanks everyone, and I'll see you in the next lecture.